Hey everybody, and welcome to another episode of Space Science with Python. Today we are going to start with our coding part for our Cassini Cosmic Dust Analyzer. So you see here a picture of the instrument I showed you last time, and I also talked a little bit how this instrument worked and also what Cassini achieved in the last couple of years. Well, Cassini is now gone since 2017, but we still have a lot and tons of data to work with. And since I worked for the CDA, so the Cosmic Dust Analyzer team and instrument, I have some knowledge I would like to share now in the next couple of weeks and months here on my channel. Now, don't worry, I will always repeat how the instrument works. I will always repeat some scientific stuff so that you will really learn it and not really have to check the previous videos. So I hope you will not get too much bored. So if it's too redundant for you, just leave a comment so I can improve these videos accordingly. Let's start with the calibration. What is actually calibration? Well, if you build an instrument or something, it doesn't matter whether it's for science, space science, or industry, or what's or not, you do not really measure directly the temperature of your environment or the acceleration or any other, for example, also chemical properties. You measure a voltage, you measure power, or you measure some kind of current or what have you. And the calibration task is now to translate these properties you measure, like the voltage or the power or so, into the corresponding physical unit you are interested in. Like, for example, temperature or the pressure or so. And the same thing applies also for the CDA instrument. So CDA per se does not measure, for example, the mass or the velocity of a particle. It measures other physical properties. And we need to translate these properties back to the velocity and also to the mass. Now, we will not talk about the mass spectrum. We will not work here in this regard today. We will only take a look at the physical properties of these dust particles. And for this, I would suggest that we are diving into a small presentation first to see how the instrument has been calibrated or was calibrated. And it's the same way future instruments are also being calibrated. So it's not like a method that was applied 30 years ago and is now outdated. No, it's pretty up to date and is still used in cosmic dust research. So I would suggest let's dive into this and then we can go into the coding part. Now here you see a dust accelerator at the University of Boulder, Colorado. So this kind of setup is, let's say similar to the thing we have here also in Stuttgart. What you see is a chamber. In this chamber we have our dust particles that are waiting to be accelerated. Here we have our pipe with a lot of different instruments. I will explain in a moment. And then we have here the chamber where the instrument, for example, the CDA in the past, was waiting for the dust particles to arrive. And a schematic drawing can be seen here. As again, we have here this chamber. This is here the chamber with the dust source. So there are a lot of different particles with different sizes and so on that are being picked up, and then they are being accelerated by an electric field. So they are accelerate already here in the chamber. Then they fly through this pipe. And this pipe we have different measurement units that measure, for example, the charge or the mass and the velocity of the particle. And you can set up the range of the particles you would like to have on your computer, and then a control unit is selecting the particles that are needed for your experiment. Now the thing is, the dust source itself cannot really pick up individual particles based on their size or so. So everything is done here on the fly, literally. And if you have a particle that is maybe too small or too large, then the deflection unit here is being activated. So we have here, we can set up here an electric field that will not allow particles that do not fulfill the particle requirements pass through. So they are then deflected and are not continuing their travel through the experiment chamber that is here in the picture on the top left. And in this experiment chamber we have CDA or another instrument, any dust instrument, waiting for the particles. Now in our calibration we will take a look at these particles I showed you last time, but these are not now the cosmic particles. These are the particles from such an experiment. And we will take a look at the different signals here from the QI channel or the QT and so on. So not really the signals, but more derived parameters that I would like to show you in the code just in a moment. I hope this gave you a small feeling and introduction on how the CDA instrument was calibrated and what kind of data we received. And I would suggest now to dive into the data, to take a look into the data frames and what kind of data do we have. So the data, they have been provided by Ralf Sramer from the University of Stuttgart, who was also my supervisor for my PhD thesis. So thanks to him, we have now the data we can now work on in this tutorial session. And I would suggest that today we will take a look into the data. We will try to understand what have been recorded. And then at the end, let's talk a little bit how we will proceed in the next 2-3 videos. So let's go into the coding. Okay, let's start with the coding part. Before we go into the coding, I want to say that I changed a little bit the YouTube setup. So normally I just write, I think every coding block here has its own section in YouTube, but I think this is a little bit too granular. So I will now use these kind of headlines here to separate it into block sections. I think this is less granular and makes a little bit more sense, so that you can that you have some sections to go through. Now let's start. Today we are taking a look at the data and do some data exploration. So I would say let's go and read in the data that we are interested in. Now first we need to, of course, import our standard stuff, yeah, the libraries and so on, also the zip file library, because the data that have been provided are provided in a zip file. And the data is also uploaded on GitHub, so you do not have to be afraid that you have to download it somewhere or so. Everything is now available also on GitHub, so just get the most recent pull, and yeah, and also do not forget to bookmark the repository so you will not miss any updates. So let's unzip the file, and everything is now extracted in the data directory level 0. Well, the file structure, you can check it out with a text editor or what have you, but I already know the column names a little bit and also the structure, so this looks a little bit like dark magic. It's not like something that I just wrote down here because it was trivial. Yeah, of course I was in exchange, an email exchange, how do the data look like? So I would suggest just define the column names, and let's take a look at the data frame itself so that we know what is really important and what not. So we have here some reference numbers and some values. They do not matter now for now, but what we see here is the so-called particle selection unit. So the part in this pipe, let's say, that selects our particles and also measures their velocity. And we see here the values are provided in kilometers per second. So we see, like here, for example, 17.4 kilometers per second, 11, 9.68, and so on. And in total, we have 4,705 events. We have also the charge of the particles here given in Coulomb, and then also here the number of peaks that the instrument measured. So as you may remember, we have this flight of mass spectrometer, and we do not have now the spectra here in the data or the signals, but we have some kind of algorithm that already determined how many peaks have been recorded, and this will be interesting for the next video. Now we see here also the acceleration speed in kilovolts, so this is like 2 megavolts, so that's quite a lot, I would say, and also different parameters. And in the very last column, you see the target that has been hit. So we have like the CAT, so the center rhodium target of CDA with the IID, and with also wall impacts. But I would suggest now to make this data frame a little bit more shorter and smaller so we can take a better look at this, because there are like 29 columns and it's a little bit too much. So I already did some work, and I would suggest to do this now here in cell number 5, where I select certain columns, so the velocity, the charge, the number of peaks, the acceleration. This will be interesting just in a moment. We take the charge from the QI channel, also the corresponding rise time of the signal. So if you remember, we have the signal that goes up and then goes down at some point, and the rise time is like, yeah, the time from the baseline to the top. Okay, it's not exactly from the baseline to the top, but let's assume it now for now. So this is like the rise time. We have the same also for the QC channel and also for the QT channel. So I know it's now a little bit confusing, QI, QC, QT, but again, just go step back a few seconds and take a look at the diagram where I was explaining the CAT, or also the last video. It's a little bit difficult in the beginning to get familiar with all this wording, but yeah, maybe this maybe you will just need to make a screenshot or so and put the schematics next to you so that you get a better understanding, as well as also the target. Now the target itself has also some other wordings, so like for example center part or the outer part of the targets, but we just replace it with the name, and then we exclude all the wall impacts. So we just consider the impacts on the larger and the smaller target here, execute the cell, and we are done. Now in the next step, what we do, I would like to convert the time into microseconds. So the rise time that is provided here is not in seconds or what have you. This is provided in tenths of nanoseconds. So this is why we have to rescale it a little bit, and also the charge is rescaled by femtocoulomb. So now I know I'm moving a little bit away from the, let's say, standard SI system, so not providing everything in seconds and column, but in the next video you will see that this kind of scaling makes a little bit of sense. So let's execute this cell here and take a look at the final data frame now. And we see the velocity of the PSU in kilometers per second, the charge in femtocoulomb. You see we have now reasonable values, you know, they are not too large or too small. It's quite nice to see that everything scatters around these femtocoulomb values. We have the number of peaks in the third column. We have the acceleration speed in kilovolt, the charge and rise time of the corresponding CDA channels, giving here in also in femtocoulomb, and here we have it in microseconds, yeah, for all the channels, and then we have the target at the very end. So this is now our final data frame, and we can work now with it and take a look what's in there. So let's go into the next block section. We check first some implausible data. So yeah, if we just check out if we have particles that have a velocity of 0 kilometers per second, well, we have some 3, so we should maybe filter them out. And if we take a look at the charge of the particle, so if we sort the data frame by the charge of the particle selection unit and plot the first 25 values, or no, the last 25 values, we see that some are quite large. So yeah, this is also kind of implausible. So I also suggest that we remove all these extreme values so that our calibration curve later on in the next video will not be messed up. The next coding block is now something that is maybe also interesting, and I think it's interesting because now we use this acceleration values, right? So we want to compute the mass of the particles, and this is possible by using simple physics equations. Yeah, we need to determine the energy of the particles, of the kinetic energy, and the energy these particles have after the acceleration phase. And for this, well, we need simply to multiply the charge of the particles. We have it. We have the charge here, PSU charge. So that's the charge of the particle determined by the acceleration device, times U. This is the acceleration voltage. It's given here in kilovolt. It's here 2000. And this this energy by the electric field is equal to the kinetic energy of the particle, and the kinetic energy of the particle is 1/2 the mass of the particle. This is the value we are looking for, times the velocity squared, and the velocity is also provided by the particle selection unit in kilometers per second. So what we need now to put both equations together and solve it to m, the mass. And if we do this, we have this kind of function. We have m is 2 times the charge times the acceleration velocity, acceleration voltage divided by the velocity squared. So this is how we can now compute the mass, and this is what we do now here. First, we need to convert, of course, the kilovoltage into voltage. So we have to multiply it by 1,000, and then we can compute the mass. We use a lambda function here in this data frame, 2 times the charge. The charge is given in femtocoulomb, so again rescaling it. So this is q times the acceleration the voltage of the accelerator. This is u divided by the PSU, the determined velocity. This is given in kilometers per second, so we have to also rescale it by 1,000 and then to the power of 2. And this is now the mass we have. So that's basically all we need to compute the mass. And we will also rescale the mass now in a second. Now I would suggest to plot our particle properties. And I would suggest let's start with the velocities so that you get really an understanding, a feeling, how does it look like, right? Because we have like no clue for now, how do the data look like. So here in this example, we use matplotlib to create a histogram of the velocity distribution. So let's take a quick look, divided in bins of 5 kilometers per second. And there you see we have a range from very small velocities to up to 50, 60 kilometers per second, with a peak here at around 10 kilometers per second. This is like our distribution. So this is how it looks like. But this is not like, this is the one thing, but we know that the kinetic energy scales also with the mass and so on. So let's see if we have some kind of bias in our accelerator. And just small spoiler, we have, and we can show it here when we plot the dependency between the mass and the velocity. So what we do here is we put the velocity on the y-axis and the mass of the particles on the x-axis, and we do it in picogram, and apply the log 10 on this masses. So of course, it's nothing you do from the beginning, right? You play around with the data and check how does it look like. And if we do it now, we see this kind of distribution, the mass in log 10 picogram and the velocity in kilometers per second. And you see that the heavier particles are potentially slower than the lighter ones. So it's not something that applies also in space. We will also have massive particles traveling also at 40, 60, 80 kilometers per second maybe. But with our dust accelerator setup, we are not able to reproduce it. So we can only accelerate lighter particles to higher speed, and more massive particles, they are slower. And this is what you see here in this graph. You see also here some kind of different artifacts or so. And one word, it's also not this kind of particles you will find in space, or some particles you will find. We have iron particles, of course, this is fine. Also carbonous particles, but also using latex particles and so on. So different types and different chemical compositions have been used to really calibrate this instrument. But here we threw everything together. Now some additional statistics at the very end. Let's have a look before we do the calibration function next time. Well, we have now in total 4,184 events, and around 1,650 are on the hit the larger target, and 2,500 the smaller target. So the CAT, where the particles are accelerated to the time of flight mass spectrometer. And now if we focus on the IAD, we have to determine a little bit the quality of the data. So let's select first the IAD target. Then we check if we have only particles with a rise time larger than 0. And also the charge is larger than 0. So this is like something divided for the QI impact and QT. And then I was also checking, okay, let's see if we have particles with a QI rise time and charge larger than 0, and also a QT rise time and charge larger than 0, just to get some statistics. And then you see here we have like in total 1,500 particles, let's say good impacts where we can do, I would say, good calibration work later on. Now the same thing applies also with the CAT, so the target that where the particles are then, or the ions are then accelerated to the multiplier, the time of flight mass spectrometer. And here we have to add another filter, namely the one where we say, okay, the number of peaks that have to be detected have to be at least have 2. So this is something in a discussion with my supervisor back then, where we really want to be sure that also our ion cloud was also hitting the multiplier, so that we were really able to detect a spectrum. So we set the arbitrary limit of 2 peaks that are needed to fulfill this requirement. And if we take a look here, we see that also we have like QC and QI impacts at 1,500. But if we really separate or consider QI and QC, then we have, and now you see here live coding. Why I do my tutorial, I made a small mistake. It has to be QC, not QI. So these things happen. Yeah, now these values make sense. We have 1,500 CAT impacts. So yeah, I should really update the script afterwards, because this was quite confusing now. Finally, we can now store our data in our level 1 folder, where we simply say CDA, CAT, IID, calibration data.pickle, and this is basically it. Yeah, this is everything we need now for our next tutorial session, where we will then take a look at the calibration functions that are already there. Well, I hope this coding part helped you a little bit to understand the data and so on. So it's not like that trivial, I would say, like, for example, machine learning tutorials that show you housing prices or temperature curves or images of cats and dogs or so. But I think you have now an understanding or a feeling how this data have been recorded and what we can do now. So the next step is now that we will take a look at the calibration functions that are already existing. So what kind of functions are out there? What kind of calibrations function have been applied? How have they been fitted to the data? And then we will take a look at the results. And then after this video, we will create a new tutorial where we take a look at a machine learning based approach. So how can we calibrate our instrument with machine learning? And there I have something prepared for you, and hopefully you will like it. So it's not really deep learning with millions of trainable parameters, but we will take a look on how or what we can achieve with very tiny models. And we will see that even this tiniest shallow deep learning models, so to speak, are really powerful and can help us to conduct amazing science. So yeah, I hope you look forward to the next session. Thanks again for listening, and see you next time.